All right, we're going to start doing some geometry with calculus. The first thing I'm going to ask you to do is find the area between curves. So that's what this video is going to be about, is finding the area between curves. So this is an example of a problem. Find the area of the region bounded by the function f of x, which is the equation 1/2 x plus 5, the function g of x, that's the equation negative 1/2 x plus 7, the equation x equals 2, and the equation x equals 8. So I've graphed the two linear functions, and now when it says between x equals 2 and x equals 8, we're talking about this is x equals 2, and this is x equals 8. So if we're looking for the region bounded by all four of those constraints, what we're talking about is this region right here. So I'm going to give you a minute to think about it. I'm going to see if you can use any of the information here and stuff you already know to find that area. So go ahead, pause. You don't need to sit here and watch me color. Pause. Go see what you can do. Okay, welcome back. I hope you tried it. I'm going to show this in parts and pieces down below. So we've got these two different graphs, the 1/2 x plus 5 and negative 1/2 x plus 7, and we're going to try to find the area of that. And I hope you use some calculus and not geometry, because the problems will not always look like this. They will not always have linear functions where you can just find the area of that triangle. So instead, what we're going to do is use some calculus. If I look at the first function, 1/2 x plus 5, I can find the area under this function using calculus by using the fundamental theorem of calculus. So this region here, I can find the area from 2 to 8 under 1/2 x plus 5 by using the fundamental theorem of calculus. So if I find the antiderivative, 1/4 x squared plus 5x, I will evaluate that from 2 to 8. So if I plug in 8 first, 8 squared is 64. 64 divided by 4 is 16. Plus 5 times 8, so that's plus 40. Minus, and then 2 squared is 4, times 1/4 is 1. Plus 2 times 5, that's 10. So I have 56 minus 11 is 45, I think. So this area is 45. I think I did my 56 minus 11. Yep. All right, now if I find the area under this, oops, yeah, that's close enough to 2. Pretend that's 2. And here's 8. If I find this area here, I'm also going to use the fundamental theorem of calculus. So from 2 to 8, I'm going to find the area under 1/2 x plus 7 dx. So I've got negative 1/4 x squared plus 7x, and this is also from 2 to 8. So this gives me, I already did a little bit of the math, I have negative 16 plus 56, and then negative 1 plus 14. So I have 56 minus 16, that's 40, minus 13 is 27. So what I'm trying to find is the area between those two graphs. Well, I've doubled up some of my area when I've done this. I have found extra area, if you will. Oh, I'm not going to do that. Forget that I did that. I found extra area because I found the area under 45, or under this top function, and the area under the bottom function. So if I subtract those two, that'll leave me what is left over. So the material that has, or the area that has not been duplicated. Because what I've got here on the second function, I'm not explaining this as well as I was hoping I would. So the area under this purple line, this is negative 1/2 x plus 7. We found this area to be 27. So if I take the entire area of 45 and subtract 27, that'll give me the area in between. You probably knew that way faster than me. So the area of the region bounded by these two functions is the result of doing, from 2 to 8, we'll take the top function, which is 1/2 x plus 5, minus the bottom function, which is negative 1/2 x plus 7. And what we end up with is 45 minus 27, or 18. 18 units squared, if you will. I didn't give you units, so you'll just use generic units. That is the area of that triangle that was in between those two. Okay, somewhat intuitive. Sorry about my little flub of my explanation, but drawing my picture helped me explain what I was trying to get at. I'm going to give you another set of functions. I'm going to give you a minute here, and I will tell you that when we're finding area in between functions, the answer is always a positive value because we're talking about how much space is taken up and not necessarily where that space is located. So with that, see if you can find the area bound by those functions. Okay, welcome back. So we're looking at this region here. Here's x equals 8, here's x equals 2. So what we're looking for was like the last one, but now we're below the x-axis. We're looking for this region. I hope you didn't just say, oh, it's the same as what's above, because of course it's not going to always be this way. So you need to find some way with calculus to figure that out. So again, I've duplicated these functions down below. And if I look at the area under the curve from 2 to 8 for this first one, if I look at this, I'm going to say that this is from 2 to 8, 1/2 x minus 5 dx. If we use, I'm going to do the fundamental theorem of calculus backwards, 1/4 or up above instead, and then from 2 to 8, that's 16 minus 40 minus 1 minus 10. So 16 minus 40 is negative 24, and then 1 minus 10 is negative 9. So negative 24 plus 9 is, wow, subtraction is my nemesis. Negative 24 plus 9 is negative 15. Now if I find the area here, I'm going to do the fundamental theorem of calculus backward, or up above, and I'm going to go up with my work instead of down with my work. So I have negative 1/2 x minus 3 dx. If I use the fundamental theorem, I've got negative 1/4 x squared minus 3x from 2 to 8, which is negative 16 minus 24 minus negative 1 minus 6. So I end up with negative 40 plus 7, negative 33. Okay, so in this case, what we have to think about is how to find the area between these two, and we're talking about a positive area. So just like we did up above, even though we're below the x-axis, I'm still going to take the area of this upper function, which is negative 15, and I'm going to subtract away the area of the bottom function, which is negative 33. So it's still the top function minus the bottom function, even though we're below the x-axis. So this would be, if I wrote this out the long way, this would be from the area from 2 to 8 of 1/2 x minus 5 minus from 2 to 8 of negative 1/2 x minus 3. So the top function minus the bottom function gave us this positive area. So negative 15 minus negative 33 is 18. That's the positive area that we're looking for by taking the top function minus the bottom function. Okay, I'm going to give you one more, and then I'm going to stop this video so that the next one will have a little more complex stuff going on. So top function minus bottom function helps us find the area between curves. So I'm going to ask you now to graph this without a calculator. So no calculator. Think about factoring. That's going to help you a lot. Without a calculator, I'm going to see if you can find the area of the region bound by those two equations. And that's it. That's the only information I'm giving you. So go. This is going to take you a little bit of time, but it's worth the time. Welcome back. I'm going to graph these. So if I'm looking at f of x, I'm going to factor this because I know it's a cubic, which helps. And I know it's a positive cubic. So I know that a positive cubic has a general shape like this. I know this second one is a quadratic and it's a negative quadratic. So a negative quadratic has a general shape like that. So I'm just going to get a little bit more information to see if I can figure out how this is going to look. So I have 3x cubed minus x squared minus 10x. We're going to first factor this. I'm going to take an x out because I can see that I can. And then I'm going to see if I can factor this. I probably should have tried to factor this before you came back. But if I do negative, so it's 36 and 5. So if I'm going to do, I'm going to do 2 here and 5 here. So now this gives me 3x squared minus 6x plus 5x is negative 1x. Okay, so it factors out to be this. I know that this function has x-intercepts then of 0, negative 5/3, and 2. Okay, if I look at g of x, I'm going to factor that as well. I can take an x out, which leaves me with negative x plus 2. I know that g of x has x-intercepts of 0 and 2. Okay, so if I start to just graph this to give me a picture of what this is going to look like. Thank you, Notability, for the positive or for the straight lines. I'm going to graph the cubic function first. I have an x-intercept here. I have an x-intercept at negative 1 2/3, and I have an x-intercept at 2. I know that generally this is a positive cubic function, so it's going to kind of look like this. I know that this quadratic has x-intercepts also at 2 and 0, and I know that this is going to be a quadratic that opens downward. This is starting to look a little strange, but if you were to continue these two functions down here, they're going to intersect again. So really what's happening is I have two different areas that I'm trying to find. I'm trying to find the area of that region, and I'm trying to find the area of this region as well. Let's talk about this light blue region first, because that one's pretty straightforward. This one, I can see that we have a boundary that is from 0 to 2. I can see that the top function, it's going to be helpful to label this. I know that the top function is g of x, and I know that the bottom function is f of x. So what I'm going to do is find the area from 0 to 2 of g of x, top function, minus from 0 to 2, f of x, the bottom function. I'm going to let you do that math. You can find the antiderivative on your own and plug things in. You're okay with that. But we have an issue on this purple region now, though, because on the purple region, I don't know exactly where we're starting. I don't know what that point is down there. So what we can do, some algebra that we can do to figure out where these two graphs intersect, is we can set them equal to each other. So I can set 3x cubed minus x squared minus 10x equal to negative x squared plus 2x. Because I know when those two are equal is when they're going to intersect. So let's solve this. Let's find out where they intersect each other. So I'm going to add this x squared over to the other side, which is great. Those both cancel. I'm going to subtract the 2x to the other side. So I end up with 3x cubed minus 12x equals 0. I'm going to solve this. So I'm going to factor a 3x out of both of those. And if I factor some more, I see now that those two graphs intersect at x equals 0, x equals -2, and x equals +3. So we already knew some of those places. We knew that they intersect, so we're going to see they intersect right here when x is equal to -2. So what I'm going to do is find the area from -2 to 0, and I'm going to go from there. So the next region, so I'll add on, so plus the area from 0 to, or -2 to 0. This time I have the cubic function is on the top. So this one's f of x, and this one's g of x this time. So it'll be f of x dx, the top function, minus the bottom function. And I'm going to let you do the math from there. Okay, that's it. Do the math, see what you can get.